Slow. Too slow. It's really too slow. Are you suffering from this? Any batch job would take several hours, tasks one after another, starting at 6 p.m. and not finished by 9 a.m. A group of people eagerly awaited the outcome. Being strained especially on critical summary dates such as end of the year or end of the month, and if there is no result, there will be an accident. It is the same situation with report and query. You click the button and then go for a cigarette or a cup of coffee, but when you come back, there is still no result yet. You become so anxious and pat the table.
How can it be faster?
Big data vendors say, distributed, use cluster.
Cluster. It's like machines don't cost any money. Moreover, I have already used MPP. This task has 5 nodes, and that task has 8 nodes. Now there are so many machines that there is no empty space in the computer room. Do I still need a cluster? Moreover, the amount of data for these tasks doesn't seem to be too large. While hundreds of millions of rows of data may sound large, it's only around 100 or so gigabytes. And this amount of data can't run well. This should be able to run on a single machine.
Yes, this should have been able to run on a single machine, but unfortunately, the SQL database really can't do this.
What else can I use other than SQL?
Use SPRUC, SPL. A single machine can match a cluster.
What is this? Can it work?
Let's take a look at SPL's record. The National Astronomical Observatory's star aggregation task has 50 million rows of data. A distributed database with a 100 CPU cluster takes 15 days to calculate, while an SPL single machine only takes 3 hours, which is 120 times faster. A bank's anti-money laundering preparation, with 3.6 billion rows of data. An 11-node Vertica cluster runs for 1.5 hours. SPL single machine only takes 26 seconds, which is 208 times faster. Surprisingly, it has turned the batch job into a real-time query. A certain e-commerce funnel operation with a data scale of 300 million rows, Snowflake's medium 4-node cluster takes more than 3 minutes and cannot get a result, and SPL single machine finishes in 10 seconds. A certain spatiotemporal collision task, with 25 billion rows of data, a ClickHouse 5-node cluster runs for 1,800 seconds, and an SPL single machine only takes 350 seconds, which is 5 times faster.
SPL looks amazing. It really beats a cluster on a single machine. Is there any magic in it?
Oh, actually, there isn't. We know that software cannot change the performance of hardware, and the CPU and hard disk cannot speed up. However, we can design low-complexity algorithms, which need less computation. As a result, the computer executes fewer actions and naturally becomes faster. For example, if a task is supposed to be calculated 100 million times, a good algorithm only needs to calculate 1 million times, which will be 100 times faster. However, just coming up with an algorithm is not enough. We need to actually write this algorithm in programming language, otherwise the computer cannot execute it. However, if the program language used is not good enough, it may be impossible to write it, and you can only bear with low speed. This kind of thing often happens when using SQL. For example, to find the top 10 from 100 million pieces of data, SQL is written with the word order by, which means sorting is required. If we really do big sorting of 100 million records, the computational workload would be huge. In fact, as long as we keep a small set of 10 members, and continuously compare and replace members in the small set when traversing 100 million data, the computational cost is 8 times less than that of big sorting. Unfortunately, SQL cannot describe such a calculation process and can only rely on database optimization. Fortunately, almost all databases can optimize this and won't be foolish enough to do big sorting. But what if the situation becomes slightly more complicated? For example, if we change the requirement to find the top 10 within groups, the SQL statement would look like this. This is very different from the previous method of getting the top 10 from entire set. We need to first use the window function to create a sequence number within groups, and then use subqueries to filter out records that meet the conditions, which is a bit convoluted. Anyway, there is still an order by here, and the operation logic is still sorting. In actual testing, it is found that for the same amount of data, Oracle calculating top 10 within groups is dozens of times slower than calculating top 10 of the entire set. Theoretically, only adding a grouping operation should only be slightly slower. Oracle is likely to have performed sorting or even external storage sorting, and the database optimization engine may become fainted when faced with slightly more complex situations. It can only execute according to the logic of SQL honestly, resulting in a sharp decline in performance. Of course, perhaps one day the database will evolve again, and encountering such a situation, it can also optimize it. But there are always more complex situations, and the evolution speed of database optimization engines is very slow. The cases mentioned earlier all have a certain level of complexity and business requirements, with a small amount of data but a large amount of computation. SQL cannot write good algorithms, and the database engine cannot automatically optimize to reduce computational complexity. For example, in the e-commerce funnel case, SQL would be written as follows. This SQL statement is very convoluted, making it very difficult to understand. Here, we just need to feel the complexity. This is just a 3-step funnel. If you want to calculate a few more steps, you need to write more subqueries, and we don't have enough space to put it here. I can't think of how to optimize this complex SQL, and it is not surprising that this SQL cannot get a result after running for 3-minutes on Snowflake cluster. Faced with complex requirements, we cannot count on the optimization engine of the database, but still need to be able to write code with low computational complexity ourselves. Then, what kind of programming language can write these algorithms? A lot, such as C++ and Java, all of which can run fast. However, for tasks like finding top 10 within groups, considering universality, it may be possible to write using thousands of lines of code, and for funnel analysis, writing tens of thousands of lines of code is also considered normal. This has no operability, and the development and maintenance costs are too high. A programming language not only needs to be able to write algorithms with low computational complexity, but the code also needs to be simple enough. It can be said that writing simply and running fast are the same thing. This is the magic in SPL. SPL has elaborately designed data objects and their operations, which enables high-performance algorithms to be written with simple code. The top 10 task is written as follows. SPL understands top as aggregation calculation, which can directly describe the algorithm mentioned earlier. It does not have order by here, and does not perform big sorting, making it much faster. Moreover, the writing of the top 10 within groups here is basically the same as that of the top 10 of the entire set, except for the addition of grouping key. The essence of funnel analysis is the complex count distinct ID. Count distinct is a major culprit that causes the database to run too slowly and crash, with a much larger computational load than common count. The traversed IDs must be saved for comparison, and when there are too many IDs, it may crash. Funnel analysis involves multiple mixed count distincts. The count distinct of each step would be combined with the count distinct of the previous step to calculate the churn rate. The SQL will have nested joins, which will occupy much more memory and increase the probability of crashing sharply. It is not difficult to solve this problem, as long as the data is sorted by ID and only the previous ID needs to be saved for comparison during calculation. No need for large lists, and the memory usage can be ignored. The running is fast and there is no possibility to crash. Unfortunately, SQL is designed based on the relational algebra of unordered sets, and the set members have no order, making it impossible to implement such operational logic. SPL supports ordered sets, making it easy to implement this method. By using SPL's ordered cursor, data of one ID can be read into memory each time, and complex calculations can be conveniently performed without involving other IDs during the process. As long as the memory can hold all the data of one ID, it is sufficient, and there is no problem calculating multiple sets of count distinct at the same time. This is the code for implementing funnel analysis in SPL. The 3-step funnel runs in 10 seconds on a single server. Moreover, this code is shorter and more flexible than the previous SQL, and adding a few more steps to the funnel is still this code. SPL can also solve the long-standing problem of database performance, join. The database usually uses the hash method to calculate join. When the data is too large to fit in memory, the hash partition buffer needs to be used, and when unlucky, a second hash is needed, which results in uncontrollable performance. Distributed joins are more complicated, and the database industry has invented methods such as broadcast and shuffle joins to convert them to single machine joins, which are very complex and have poor performance. Some databases only implement in-memory algorithms for better speed, so it's not surprising that they crash when the data volume is large. The spatiotemporal collision case mentioned earlier had self-joins when written in SQL, and a single node ClickHouse crashed at once. It took more than 30 minutes for a 5-node cluster to get the result. In fact, the vast majority of join have primary keys involved. We can use this feature to classify join and optimize them separately, fully utilizing primary key features to reduce computational complexity. However, SQL's definition of join does not involve primary keys, and this feature cannot be utilized to optimize performance. SPL has changed the definition of join, allowing for the utilization of primary key features. The calculation of spatiotemporal collisions with the same amount of data requires only one node in SPL code, which can be completed in less than 6 minutes. There is no trace of join in this code at all. After changing the join definition, SPL can integrate join into other computational steps. Here, A3 is creating a dimension table, and the expression in A4 is equivalent to the filtering effect of inner join. The join here is a small dimensional table associated with a big fact table. SPL uses orderliness to convert foreign keys to sequence numbers, directly using sequence numbers to locate dimensional table records, avoiding hash calculations and comparisons, further reducing computational complexity and improving performance. SPL has more high-performance algorithms that significantly reduce computational complexity. These with asterisks here are SPL's original algorithms. SPL actually provides cluster computing solutions, but in performance optimization cases, single machines are already sufficient in most scenarios. Its cluster functionality has never had the opportunity to be experienced. So SPL almost never advertises its distributed functionality. Reducing computational complexity is the key to improving the performance of big data computing, but many low-complexity algorithms cannot be implemented using SQL, and we also cannot count on Database Optimizer when facing complex situations. The cost of implementing using high-level languages such as Java and C++ is too high and lacks operability. SPL can use simple code to write high-performance algorithms. In many performance optimization cases, SPL single machine performance far exceeds that of the original cluster. Less resource consumption is the real green and low-carbon technology. SPL is currently open source. Welcome to download and use it.